Hello, my name is Kwang Subsi. Currently, we are working on offshore wind energy substructures for both fixed type and floating type. Today, we'd like to talk about a tentative result of our research on the dynamic behavior of fixed supported offshore wind energy substructures, analyzed by means of XC software that we developed for this purpose. The first one is the background of this research. So as everyone understands that we have, because of global climate changes, now the energy paradigm is shifted to renewable energy. And among different resources of renewable energies, we focus on offshore wind energy because the offshore wind energy, we can minimize the environmental impact. Depending on the depth of seawater, we can consider, roughly speaking, two different types of substructure types. The first category is the fixed supported ones, and the second one is the floating types. Although we are doing research on both types of substructures, today we'd like to talk about the fixed type substructures installed in shallow sea depths. Typically, we can consider monopile, which is most popular in the world, and then also we can consider jacket and tripod. In the case of Korean Sea and the Chinese Sea, because of soft foundation condition, instead of monopiles, we may also consider the application of jacket and tripods. Okay, here are the contents of my talk today. The first one, I'd like to provide a general introduction to our program that we developed for the analysis of offshore wind energy substructures. And the second one is the information of the offshore wind energy structures that we consider in this study. The third one is the effect of wave instant angle with respect to wind direction. And then the conclusion of my talk. The first one is the information of X-Wind package. The X-Wind package is a specialized program for the analysis of offshore wind energy substructure, and as well as we can use this software package for the analysis of various kinds of marine structures. And this package consists of 5 different modules. The first one is the XC module. The XC module is for the finite element analysis. And then this module is tested for various kinds of nonlinear behavior. And also it has a strong pre and post processors. And then the second one is the mooring tools. It can model various kinds of mooring models, like for catenary cables on the fixed type and pile type mooring tools. And then also the third one is the X OpenFast, and it provides graphical user interface to NREL OW2 analysis software. So using this X OpenFast, we can combine different kinds of analysis modules here. And the XNemo is for the analysis of the behavior of ocean, like wave and current, by means of diffraction theory. And then X-anchor this is for specially we use for the anchoring behavior, and then it provides support condition to mooring tools. And all these 5 different modules form the X-Wind package, and these individual packages can be work independently, or it can work all together in X-Wind platform. Another noticeable point regarding X-Wind, the X-Wind is implemented in AutoCAD environment to maximize the graphical user interface. To build a model for this analysis, now we don't have to use any separated preprocessors from the CAD program. We just use AutoCAD environment, and then we can build a computational model from the object built in the AutoCAD environment, and then we can run the finite element analysis. And this is a feature of XC for the structural analysis. As you see here, we can take advantage of very strong pre and post processors for the fixed supported structures, and then also the floating types too. And then these floating types are under research funded by the government. And using this program, we can check the fatigue limit stays, and then the ultimate limit stays at the same time. And then here to build a computational mesh, and we adopted GMesh in this system. Using the GMesh, and we can build high quality computational mesh for both frame and shells or three-dimensional continuum too. And then now this Xwind and XC are open to public. So you can download the program from GitHub, and also for the detailed information of this program, that you can try YouTube, and also you can visit the homepage of the developer called XFINAS-IT, operated by Professor Kim here. And for the theory manuals, and you can refer to these two different research publications. And this program was verified for different problems. For example, for this nonlinear deformation, this program is verified. And then this is only one example. In total, is more than, I guess, 50 different verification examples that we tested. And then this program is tested with respect to the SAX program, specialized for offshore and the marine structures analysis. And then the generation of finite element model for the offshore wind energy substructure is very easy, because in the case of a fixed type of offshore wind energy substructures, so we may want to use either of the monopile or tripod or the jacket types. That's why these three types are popularly used. And then we provide the canonical forms of the structural system using parameters like the number of blades and number of chord, and then the diameter and thickness. And using those parameters, with this information, so we can build our computational mesh very easily. For example, we provide this example template for 20 meters and 45 meters and 50 meters, and then we were able to generate this computational mesh for our own problems here. And then as the solution option, we may use either of two different solution options. The first ones, we can model the tower top displacement. Here we apply the moment and thrusting forces and the wind load applied to tower, and or we can model only the substructures here. Then we apply the forces TP point to top of substructures. So in this study, so we use the first option. The behavior of rotor and nacelle assembly is simplified, lumped to one point here. Then we apply the thrusting forces calculated by the open fast. Now the structural types that we consider in this study here. The first one is site conditions. As a site conditions, so we consider the Yellow Sea area of the southwest coast of South Korea here. And then as the design codes, we'd like to refer to DMVGL 0437 for load and site conditions. And then also DMV OSJ 101 for the design of offshore wind energy substructures. And then also the IEC code for wind energy generation systems. And then the reference site condition, design water depth, we considered 50 meters here. And then we consider the information wave, and then also current, and then the wind conditions. Wind conditions, total average is 7 meters, and the reference wind speed for the designs around 43 meters per second. Actually, if you open the DMVGL design code, we need to consider many different kinds of design load cases. But obviously, the handling that many number of design load cases is not necessary for the research purpose. So here we consider only two different design load cases, DLC 1.1 and DLC 6.1. These two are for the normal condition. The first one is power production. The second one is the abnormal condition. Here, the power is not produced, and then the turbine is parked condition, standing still or idling condition. Now this is informational model. For the turbine data, we use NREL 5 megawatt turbine data, so 5 megawatt, and then this information of turbine current speed 3 meter per second, and the rated wind speed is around 11 meter per second. And for the details are referred to literature. And then this is dimension of structures that we consider here. Total from the sea bottom to the tower sea bottom to the TP point is around 88 meters, almost 9 meters high structures for the monopile and the tripod, and then the jacket type here. And as the material properties, because we consider steel, and this information of steel is S355. And then this is density and the elastic modulus, Poisson ratios are given here. And then this is the comparison of XC result to that of open fast for these three different types. The black curve represents the result from the open fast, and the red curve represents the result calculated from the XC. And for the monopile and then tripod and then jacket, we compared the tower top displacement. In all these three cases, they are very close to each other. But in the case of tripod type, there is a little difference, except for these, all these three types are very close to each other. And then here for foregoing discussion, so we do not use the initial 30 seconds response because of numerical instability. The same phenomena found both in open fast and XC. And this is a resonance check of substructures. Here, according to IEC code, for wind model, we use Kaimal spectrum model, and for the wave model, we use Jones-Swab spectrum model. So if you plot these two models here, the green part represents the wind model, wind spectrum, and then here pink spectrum represent the wave spectrum, which means the natural frequency of our substructure should be avoided from this spectra of wind and then the wave spectrum, and at the same time, so we should avoid our rotor frequency and then 3 times of the rotor frequency too, because of blade passing frequency. When you consider all these 3 cases for the monopile and tripod jackets, the problem that we consider in this study all are safe from the resonance check. And then these are the internal forces of the substructure at the model line point here. At the model line point, because the internal force is the maximum, that's why we need to check the internal force at this point. And in normal condition and abnormal condition, we check the change of internal forces for various conditions. So make sure that the jacket has 4 legs. That's why we check, the internal forces for leg 1 and leg 2 and leg 3 and leg 4. The tripod has 3 supports. That's why we check the internal forces at these 3 positions. In the monopile, it has only 1 support. We check the shear force and the bending moment. But when you hear the bending, obviously the bending moment would produce more significant stress. In the case of monopile, for both normal condition and abnormal condition, the internal forces are significantly higher than the jacket and the tripod. And then in the XC programs, we can check the stress unity ratio very easily. We can see the graphically at various structure positions. We can check the unity ratio very easily. The unity ratio is defined as the maximum stress divided by the allowable stress value. And for safety, this value should be less than 1. And the third one is the effect of wave instant angle with respect to wind direction. In the normal condition, here we check the tower top displacement for the monopile and tripod and jacket. According to IEC condition, there is wind wave directivity guidelines. So according to this, if the wave direction is deviate from the wind direction, the structural dynamic response should decrease. This is the wind wave directivity given in IEC 61411 code. When we compare the change of the fore and after displacement at the top position, in all these three structural types, that response decreases as the wave incident angle with respect to wind direction increases to 180 degrees. But that trend is more noticeable regarding the monopile. The change is almost about 20%. The change is significant in the case of normal condition. But in the case of abnormal condition, a very interesting feature is found here. In the case of monopile, as the wave direction changes from the wind direction, the fore and after displacement at the tower top positions increases, which means that doesn't satisfy the wave directivity guideline given in IEC code. And also, the similar trend found in tripod, but in the case of jacket, no such behavior was found in the case of jacket. But only in the monopile and tripod, the behavior not conformal to wave directivity guideline given IEC 61400. Maybe I think it's due to the abnormal condition. The thrust caused by the wind load is very small because this is idling state. But wave loading produces the structural behavior. That's why the fore after displacement difference increases. The S wave incident angle changes, becomes opposite direction to the wind direction. Now here are conclusions of my talk here. The XC and X-wind are specialized for offshore windy energy substructures in which aero and hydroservo elastic behaviors are coupled each other. Here we can consider both fixed and floating offshore windy energy substructures in this analysis package. And the dynamic response of tripod and jacket structures is less influenced by the wave incident angle in the normal and abnormal conditions because of high stiffness, and it complies with the wind and wave directivity guidelines given in the IEC code. The dynamic response of monopile structure is more influenced by the wave incident angle. In the case of normal condition, the tower top displacement by the same wind and wave direction is around 20% greater than that under the opposite and wave direction. But in the case of abnormal condition, the dynamic response of monopile does not follow the rules given in IEC code. The monopile and tripod and jacket structures tested in this paper all meet the design requirements of natural frequency, top tower displacement, and allowable stress on offshore wind energy substructures. In the same environmental load, the dynamic response such as the tower top displacement and internal forces at the motherline of monopile and tripod structures are greater than the jacket structure. The jacket structure may be more suitable for offshore wind power construction at 50-meter water depths along the southwest coast of South Korea. Thank you for listening.